Hi everyone. Thanks for joining the talk. I am excited to share with you what we've been doing in my lab, Icon Lab at UC Berkeley, across different robotic applications, from warehouse robotics to manufacturing to using drones. But a common theme among all the applications that we are interested in is we are really hoping to make robots capable of safe and intelligent interactions with other agents. We want to make sure that robots are capable of interacting with other robots, or they're safe and intelligent enough that hopefully soon when I go back home and I want to unload the dishwasher, the robot is going to be there and it's going to be capable, which is going to be tough. But I don't think I need to motivate too much for the people in this audience why these problems are hard. If you check out news headlines, there are always news about robots doing something crazy out in the world, in unstructured world around humans. Here is one example of recently a robot just went crazy in a restaurant, and then you can see that essentially people are trying to shut down the robot to just get it under control. I actually encourage you to watch the video. I couldn't, unfortunately, download the video to have it in, but it's just the robot just goes crazy, and then people and the customers are very scared by seeing the robot. For those of us in the Bay Area, we've probably heard a lot about autonomous cars and things that happened in San Francisco with autonomous cars. And a lot of these examples are an indicator of the fact that human-robot interaction can be hard, particularly when there are pedestrians and humans agents. But that is not specific to only human and robots being hard. Even multiple robots are really hard. Here is just one. There are actually many of these videos if you look them up. This is quite a recent one, which is the 3 Waymo cars in San Francisco, essentially not knowing what to do around each other. They're just like stuck, and then no one really knows how to get out of it. And then the traffic essentially gets worse. You can look for many videos of this. One famous example being the recent, actually not that recent, maybe from a year ago or 2 years ago, the honking in the Waymo parking lots. Here is another video, which is kind of my favorite, which are these Amazon robots. They're stuck. They have no way of getting out of this situation. They are stuck in a standoff. And I feel really bad for them. And they're just like some innocent robots. They are trying to move to their goal, but it is hard for them to coordinate with one another. And this is something close to what you may experience if you're walking down the hallway and you run to your colleague, but eventually you manage to figure it out. But for these robots, they're just stuck. So what we work on in my lab is really across 4 different domains in terms of control, learning, perception, and safety. And we are looking for how can we make sure that these things are not going to happen? How can we avoid these outcomes? How can we make sure that the robots are going to be integrated very much like how humans essentially interact with one another in our society? So unfortunately, I won't get to talk about all these lines of work. And my hope is that essentially give you a summary of what we've been doing in terms of control and planning and learning, and briefly talk about some challenges associated with safety and perception. But let me start by what makes control and planning in these domains hard. Why is it that making a decision when there are other agents involved is a difficult problem? One of the main reasons that this is a hard problem is that if you want to interact with others, if you think about it, you need to reason about the likely reactions of others to your own decisions. A robot that is trying to essentially navigate a hallway needs to reason about how others or humans will react to the decision of the robot and take that into account when making its own decisions. When you are changing lane, when driving your car, you have a mental model of what other drivers do. You're like, if I nudge in and if the other vehicle slows down, that is probably an indicator of the fact that I can change my lane. So we want to have the same reasoning capability for robots. And I call this robots being required to have joint prediction and planning. That the robot needs to account for how others will react to its decisions and take actions based off of that. And that's what we do as humans a lot. That is something called theory of mind. But, okay, that's cool. We want robots to have that. But how? How can I mathematically formalize the need for joint prediction and planning? How can I essentially have algorithmically design these for robots? I'm going to explain this at a very high level, how we formalize this. Let's say we have a number of agents, some of which are humans, some of which are robots. And each one of these has a goal in mind. They want to accomplish a task. Let's say they have a goal position that they want to go to. And then each one of these robots is a dynamical system. They have a notion of a state and the notion of control input that evolves in time based on how the agents take decisions. And each one of these agents, let's say, has a cost metric that they want to optimize. And the cost is essentially capturing what that agent wants to do. For example, agent 1, if they want to reach their goal, they might be minimizing the distance to their goal position. However, the challenge that arises in decision-making in these multi-agent domains is that no single agent can optimize things on its own. It is, in this case, if, for instance, it's a navigation task, Robot 1, if it gets too close to Robot 2, that will incur a high cost, that will incur a high collision cost. So it can't be that the Robot I essentially optimizes for its own decisions regardless of what others are doing. In other words, agents' decisions are interdependent. What one agent does is going to affect the other agent and vice versa. So how do we study these problems? I can't optimize, let's say, JI on its own. So what's the right way to formalize this? People have studied these type of multi-agent problems extensively in the game theory, economics, finance, controls literature. And they've found out that in a lot of these multi-agent interactions, a good solution outcome for modeling that joint prediction and planning capability that we wanted in the first place can be captured by seeking the equilibria of the dynamic game. What does an equilibrium mean? This equilibrium is in a game-theoretic equilibrium, not a control-theoretic sense of equilibrium where the derivative is 0. So at an equilibrium, the idea is that essentially agents will have joint prediction and planning. In particular, there are many types of equilibria, but the one which is most relevant to robotics are Nash equilibria, where the idea is that essentially every agent predicts how others are going to behave, and based on that prediction, takes the best possible action that it can. So it is mathematically elegant, and mathematically speaking, an equilibrium is a set of actions that say UI stars, such that at equilibrium, no agent has any incentive for changing their action to some other action. So for agent I, every agent I, there is no incentive by going from UI star to some other action UI. In other words, every agent is doing the best that they can in response to others, and no agent is going to change their strategy. So it is elegant. It models the joint prediction and planning capability that we originally wanted. But the problem is that computing these equilibria is really hard. So finding such equilibria means that you need to solve essentially a bunch of coupled optimal control problems. And for robots, which are typically nonlinear systems, nonlinear cost functions, you need to solve coupled nonlinear optimal control problems, typically in real time in a receding horizon fashion. And that's very hard. So effectively, we have a solution concept, which is very powerful, but computing it is a challenge. And several works have looked into, okay, how do we get around this, including the pioneering work that Mac did on how can we essentially get around computing these equilibria. And for a while, I was spending a lot of time thinking about this problem. And I was thinking, okay, this is a powerful solution concept. It models how humans make decisions pretty well, but we can't compute it that easily. That doesn't make sense. Maybe there is something about this problem that makes it easy. Maybe there is some structure in this problem which makes it easy for us as humans to take actions which resemble equilibria. It turns out there is actually a structure in these games which simplifies the problem of finding equilibria in them quite significantly. And in particular, it turns out that a lot of these real-world interactions that a robot would face become an instance of a simpler class of games called potential games. Potential games are a very well-studied class of games in game theory. I'm not claiming that we developed them. They're just very well-known and established class of games. And they have a number of interesting properties. And perhaps the property that is the most relevant to us is that if a game is a potential game, instead of solving those coupled optimal control problems for finding equilibria, we can just solve a single optimal control problem, which is the problem of minimizing the potential function of the game over the entire state and actions of all the agents. And that gives us the equilibria of the original game. And what we showed was that in a series of works, we showed that many of these real-world interactions that we deal with are typically an instance of a potential game, so they're much easier to analyze. But let me explain what it means for a game to be a potential game through a very simple high-level example. Let's say I have 3 agents, and each one of them has a cost function. Let's say agent 1 has a cost function which is composed of the tracking costs of agent 1, plus some collision avoidance costs, which essentially penalize agent 1 from getting too close to agents 2 or 3. And let's say all the other agents have the same cost structure. Let's start with a simplifying assumption that if agents 1 and 2 penalize for collisions with each other symmetrically, meaning that agent 1 penalizes for collisions with agent 2, the same way that agent 2 penalizes for collisions with agent 1. And if I have such a symmetrical relationship for all pairs of the agents, it turns out that you can simply find the equilibrium of the game by minimizing a potential function, where the potential function is simply the sum of the tracking costs of all the agents plus the pairwise collision avoidances of the agents. So the problem of finding an equilibrium in this case for me reduces to minimizing that potential function subject to the overall system dynamics. And now this is a single optimal control problem. I can use any trajectory optimization that I want for solving this. No need to worry about game solvers. And we can essentially show that we can run this in a receding horizon fashion on systems like quadcopters. This may not be impressive as of now, but at the time we were like, oh, we can run this on a quadcopter, amazing. And then we essentially benchmarked the savings that we get with our reduction to a potential game. And we found that on average, compared to existing solvers for finding equilibria, we are 20 times faster for a 4-agent setup. But the savings are just going to increase as we increase the number of agents. So we were excited. We were like, OK, great. Now we can solve these more reliably. We can solve them really fast. But we were like, OK, how far can we go with these potential games stuff? And in particular, we were like, OK, we could solve these problems, but there were no explicit constraints in these problems. I kind of cast collision avoidance as a cost, as a penalty, not as a constraint. What if the robots are just subject to some explicit constraints that they must satisfy? Let's say I have 2 robots that they want to transport a rigid object. They're subject to an equality constraint that they must satisfy at all times while sharing an environment with humans. This, again, maybe for us is easy, but for robots it's really hard to do, because to do this, to transport this object to its final position, the robots need to reason about humans' reaction to its decision and also make sure that they maintain this constraint at all times. So we thought this is actually a good challenge experiment for us to make sure that we can handle higher dimensional systems and constraints. But at the same time, since I was a kid, this scene from the Cinderella movie has been my inspiration. Like the birds essentially helping her get ready, they fly around, bring things to her. And like even now, every time I can't find my glasses at home, which is very common, I'm just like, when can I have my crazy flies just fly around, bring things for me? So we're just thinking as a first step towards that, can I have 2 quadrupeds, 2 crazy flies in this case? They're attached to one another through a rigid object. And we've asked 2 of the students in our lab to just be like, go to essentially a position that we specify for you ahead of time, but that's the only information that we give them. We're just like, navigate to your goal position, and let's just see how the drones will figure this out, how they can manage their motion around humans. And this is what we found, which is, we found that once the agents get close to each other, the drones kind of quite elegantly change the orientation of the rod and manage to essentially allow the humans to take over, or one of the humans essentially takes over, the other human stops. But it all happens because of that game-theoretic kind of reasoning in them, and because they can run it really fast in a receding horizon fashion. So we were very excited by this, and we were like, oh, okay, now we can do really closer to real-world applications with game-theoretic solvers. But then I was actually attending a conference, a CDC conference in Singapore, and one thing hit me, which I realized that, okay, so far, I've discovered how to find one equilibrium, but interaction equilibria are not unique. Like, think of two agents. One way for these two agents to avoid collisions is for both of them to yield to the left. One way for them is for both of them to yield to the right. And both of them are equally good. The problem happens when one decides to go to the left, the other decides to go to the right. And that's when essentially agents are not coordinating with one another. And that is exactly what happened to me in Singapore. First day in Singapore, I noticed that I'm just constantly running to people and bumping to people. And it took me a day to realize that the convention in Singapore is to just yield to the left for avoiding collisions, whereas here in the US, we yield to the right. So both of these solutions are equally good, but they are good as long as all agents pick the same equilibrium. Otherwise, essentially coordination is lost. So we started to think, actually, you know what? It really matters for a robot to understand what mode of interaction a human is picking and adapt to it. Otherwise, the robot is just doing its own thing and ignores the conventions or the social norms that are inherent in humans' decision-making process. So we were like, okay, how does this work out? We thought that, you know what, maybe now that I have this potential game structure, I can essentially try to find all the local minima of my potential function. Maybe that gives me a list of all the equilibria or local equilibria that the agents have. And then in real time, the robot could just be like, okay, let me try to see among these lists of equilibria, which one the human is picking, and just adapt to that. Think of it as essentially exploring the solution space of an optimization problem and being like, oh, this person is preferring this optimizer. And by something as simple as that, we can essentially, the robot can do something that I couldn't do in Singapore. My student is navigating around the robot. The robot doesn't know which convention wants to pick. But in real time, once it essentially deviates to the left, the robot knows that it should pick the other equilibrium and vice versa. But the interesting part to me was when I was thinking, okay, we just figured out there are two equilibria when two agents are around each other. But what if I have two agents and one obstacle in between, and they want to swap their positions? And let's imagine that the agents only get to see each other once they get closer to each other than a threshold. How many equilibria do we have? How many possible ways do we have for these agents to coordinate with one another? When I was thinking of that, I was naively thinking, okay, there are just four equilibria. They can coordinate in two ways when they both go to the top or to the bottom. It turns out, after running the solver, we realized that there are 6 possible ways for these agents to coordinate when there is an obstacle in between. When they both go to the bottom of the obstacle, there are 2 ways for them to coordinate. One yield to the other. When they go at the top of the obstacle, there are also 2 ways. And there are 2 other possible modes, being one going to the top, the other one going to the bottom of the obstacle. But I couldn't think of it ahead of time when I was just thinking about the equilibrium. But with just essentially running the solver, we managed to show that you can recover these interaction modes that may not even be intuitive at the beginning. At least for me, they were not intuitive. So the message for us has been that if you have a good model of your agent's dynamics and your cost functions, then your robots can plan really efficiently by leveraging this structure which is inherent in these interactions. By leveraging the fact that these games are typically potential games, there's a lot that you can do. Essentially, you reduce the multi-agent planning problem into a single-agent planning problem. So that's all great news, except for the fact that essentially when I started the talk, I started with this slide of showing you the agents and saying that every agent has a cost function that they want to optimize. And I implicitly assumed that I know everything that I need. I assumed that I know the agent dynamics, and I assumed that I know the cost function of every agent. And a very reasonable question to ask is like, how do you know what objective function the humans are optimizing for? Like in the video that I showed with the quadrupeds navigating around humans, how would you know what is it that the human is trying to optimize for when I ask my students in the lab to move to their goal position? So this is a problem that we actually worked on with Mac. We spent a lot of time thinking about this. And we spent a lot of time reading the literature on this, of like, how do we even know what is it that a human is optimizing for? So as you may probably know, this is a very well-studied problem in reinforcement learning literature known as inverse reinforcement learning, where the idea is that you collect demonstrations from a human, and under the assumption that the human is noisily optimizing a cost function, you try to learn and infer the underlying cost function of the human. And mathematically, modeling the human as a noisy optimizer of a cost function means that you assume that human has a policy pi that takes an action u, which is proportional to the exponential of the expected cost, the exponential of negative expected cost associated with it. Intuitively, it means that the higher the reward of an action is, the more likely it is for the human to take that action. But it adds this noisy decision-making process because if you collect data from humans, which I think many of you have already done, you know that humans are noisy. Humans are not going to behave deterministically when you collect data from them. That's great. So people have studied this. But it is assuming that you are learning from a human in isolation. You're just looking at a human, no other agent around the human, and you want to learn from them. And my argument is that this may not be a good way of learning about how humans interact with one another. And my argument is that because agents' decisions are interdependent, we need to account for agents' interdependence of decision in the cost learning phase too. And instead of learning from a human in isolation, we want to learn from demonstrations of interactions between humans to infer their cost function. Think of like a student that wants to work with me, and they want to learn about my objectives as a professor. If they just collect data from me working at my office, that doesn't really reveal much about what type of an advisor I am. And the smart way is to essentially go collect data and watch me when I'm interacting with my students. That probably reveals a lot more about my advising style or whether a student should take the risk to come to work with me. So I want to argue that the same thing is true about humans too. If you really want to know how a human interacts, you'd better watch them in their interactions. You can't just guess that by seeing how they essentially function on their own. So with Mac, we thought about this problem for quite a while. It's a very hard problem, but we were thinking about if I have demonstrations of multiple agents interacting with one another, how can I infer what is it that each agent is optimizing for? And the first question that we had to deal with was that, okay, we know from the literature in IRL that humans are always noisy. How can we even account for that noise in the data that you get from multiple humans interacting with one another? So we ended up reading a lot of papers in cognitive science, philosophy, and we took inspiration from an idea in cognitive science called quantal response equilibria to use that as a modeling paradigm for modeling noise and suboptimality of human decision-making in multi-agent interactions. So the idea in quantal response equilibrium is that people collected data of actual humans in laboratory experiments, and they were like, can we explain humans' decisions from a game-theoretic perspective? And it turns out you can explain it, but through a noisy version of Nash equilibrium, where every agent is maintaining a probability distribution over their actions, and there is a fixed point for those probability distributions. There is even this quote that if Nash were a statistician, he would have probably discovered this notion of equilibrium instead of the usual Nash equilibrium. So we were like, okay, great. People have seen that this explains humans' choices. Maybe we can build on it and make it be a useful concept for these robotic tasks. But the first thing that we needed to essentially face was that this notion of equilibrium is developed only for static interactions. We just take a decision once and that's it. So we started to think, how can we extend it to dynamic games? It turns out you can essentially extend quantile response equilibria to dynamic games through the notion of a Q function in multi-agent setup. So every agent maintains a Q function, Qi, and if we marginalize the impact of all the other agents' policies, kind of having like an expectation over the Q function of every agent with respect to the policies of others, then at equilibrium, we essentially want to have the same exponential property that we saw in a maximum entropy principle. So at equilibrium, the probability of taking an action by each agent I is proportional to the expected cost that is associated with that state and action pair. The only difference is that this Q bar in my exponential is essentially averaging out the policies of all the other agents. We studied this notion of equilibrium that we call entropic cost equilibria, theoretically. And the reason we called it entropic cost equilibrium is that it turns out this notion of equilibrium is exactly the extension of maximum entropy principle to multi-agent settings. Those of you who worked in RL, you probably are always using a maximum entropy or an entropy term in the objective function of your RL. This is essentially the multi-agent extension of it. And it turns out that for a certain class of games, this can be found in closed form, so it has nice analytical solutions. On top of that, the nice thing about entropic cost equilibria is that it allows you to model how rationally agents are interacting with one another. I can essentially add a weight parameter beta I to my entropy term, and then by changing that, I can model how irrationally or rationally the agents are behaving. For example, one interesting thing here is that as I make the agents be more irrational, you start to see that there are more noise in trajectories of two agents navigating around each other. So there is a lot of noise in these trajectories. And the other interesting part to me is that there are new modes of interaction that emerge by considering bounded rationality of agents that you couldn't explain if you assume that agents are perfectly rational. So for making sense of certain decisions made by humans, you really need to factor in that they could be irrational to some extent. So we use this kind of modeling principle and use that in the context of IRL. We were like, through the usual approach of, let's do a feature matching. Let's assume that our cost function is a combination of a set of features. And we want to learn the weights on these features such that the expectation of these features under the demonstration data is the same as what my model predicts. So the high-level intuition behind this is that I want to make sure that my policies are going to be as close as what I've got in my expert demonstration. And we've tested this on a number of data sets, tested this algorithm on a number of data sets, but I just want to quickly show you the results of the recent study that we ran with this, where with UT Austin, colleagues at UT Austin, we had cameras on the campus, watch out when you're walking on campus, and collected them trajectories and observations of trajectories of pedestrians on campus. And we used our model to see how well we can predict humans' motion and how humans behave around each other, particularly on a campus where there are many people around each other. And what we found was that compared to the state-of-the-art imitation learning algorithms, we are doing a much better prediction of humans' motion. We are doing a much better prediction and much more accurate prediction of how agents are essentially moving around each other. In this table, in this plot, the y-axis is the prediction accuracy, so the smaller it is, the better it is, and the x-axis is the time step. So to us, this was an indicator of the fact that in a realistic setup, when I don't have the luxury of collecting many information about the humans, and I just collect a handful of demonstrations, imitating the reward or the cost function of the humans can be very effective for predicting how are they going to interact with one another. But you may argue, why are you going through all this challenge of modeling the reward function? Why not just imitate the policies of the agents and not worry about the reward function? So if you have a ton of data, which we hear a lot about these days in robotics, I collect a lot of data from agents interacting with one another, and I just try to directly imitate the policy and essentially do behavioral cloning on the policies. So we were like, that's very easy. That's obviously very cool. So we started to theoretically study that, and we were interested in this question of how is behavioral cloning in a multi-agent domain different from single-agent domain, if any. We didn't know what differences it has. So we were like, I have a set of agents. Agents take actions, and then each one of them receives a reward, and then the environment moves to the next state, and I collect all this data, and I want to imitate that policy. The usual approach in single-agent imitation learning or behavioral cloning is that people kind of define something like a value gap, which is how much am I losing in my value function by not learning something which is the expert policy. Like by just approximately mimicking the policy, how much am I losing? And this value gap is really the suboptimality that each agent is experiencing by playing a policy pi instead of the expert policy pi IE. But it turns out that in multi-agent interactions, this value gap is not the only thing you should care about. It turns out that there is another issue that comes up when you want to do multi-agent imitation learning, which is called the exploitability of policies that are learned. And this is not a thing that exists in single-agent imitation learning. Essentially, the exploitability of policies is kind of capturing how much regret agents are going to experience by taking an action which is different from the expert action in response to the actions of the others. So this exploitability is really capturing the fact that now, when I have a multi-agent setup, I have the option, I have the autonomy as an agent to react to the suboptimal policies of others. It's not like others are part of the environment. If they're playing suboptimal policy, I can also react to that. And it turns out, if you want to have policies which are not exploitable, you need to have full state support and exact matching of state and action occupancy measures. So you really need to make sure that all the states of your system are covered. And all pairs of state and actions, if you're in finite state and action spaces, you have a perfect and exact match state action occupancy measure. And that's a very, very, very strong assumption. And the lesson for us was that if you really want to imitate policies in these interactive behaviors, you really need to put in a lot of structural assumptions, such as dominant strategies, which is like a term in game theory. It doesn't really matter, but it's this strong assumption saying that essentially no agent is going to deviate too much by reacting to others. So the difficulty arises from the fact that in a multi-agent setup, the moment one agent is slightly different from their expert strategy, the other agent could react to it. And then this could continue to the point that you're far off from the distribution of your training data. So this to us was kind of like a theoretical study showing that single-agent imitation learning and multi-agent imitation learning could be different on certain aspects. But I want to make the whole thing even more complicated by saying that this result, that I'm saying that under the assumption of full state support and state action occupancy measure matching, all of this is still for the fact when I just have like one equilibrium that I'm trying to imitate. So if I have just one equilibrium of interaction that I want to imitate, that's kind of the assumptions that I need. But I motivated for you that a lot of these multi-agent interactions are multimodal. Mode in the sense that there are different ways that agents can coordinate. So you could argue, okay, I could imitate the data that includes two modes of interaction, but that doesn't mean that my policy could generalize well to 4 other modes of interaction, because it just has seen that. Whereas by learning the reward functions, I could essentially recover these modes of interaction. But we were like, okay, this is very classical of behavioral cloning, that you want to make sure that all the behaviors that you want to imitate are in your demonstration data. So let's say my demonstration data contains all the equilibria, all the interaction modes. There are like sufficient coverage of all that. How can I learn policies that essentially model multiple modes of interaction? Classical learning algorithms, as probably many of you know, if you just train them on these multimodal data sets, they're just going to do mode averaging, and they're going to collapse. So inspired by the success of diffusion models in capturing multimodalities and trajectory optimization for robots, we started to think, how about we use diffusion policies to learn multiple modes of interaction? Can I use diffusion policies to get robots or agents to sort of implicitly coordinate with one another, depending on what mode of interaction each of them is picking? So you may be thinking, okay, we've seen this many times, that diffusion is great in capturing multimodality compared to its alternatives, but what's different here? The thing which is different here is that I need to have decentralized policies. I want to make sure that every agent makes decisions on its own. So what I do is that I collect a data set that contains all of the kind of interaction modes, and then I jointly train the policies of the two agents together, but making sure that those policies can be executed in a decentralized fashion. What does that mean? Let me show that through a context of, let's say, an example. So the two robots need to collaboratively lift the object, but there are really two ways for them to essentially coordinate with one another. One is to move to the left of the obstacle. The other is to move to the right of the obstacle. And let's say I want to make sure that these robots have decentralized policies, meaning that each robot makes decisions on its own. It's not like a central coordinator telling them what to do. If I have this data in my data set, how do I recover a policy that each robot learns such that on the fly, the robots can coordinate with one another? And it turns out, by having essentially a decentralized version of diffusion policies, you can recover something that resembles that. That essentially here on the left, you see the video of the robots picking up the object. You can see that the basket is essentially stretched between the two of them because there's no explicit communication between them. But on the right video, they essentially managed to coordinate on the different mode of interaction. And the interesting thing to me was that across multiple rollouts of these policies, it was like a 50% chance. 50% of the times they coordinated and ended up moving to the left of the obstacle, and 50% of the times they essentially moved to the right of the obstacle. But so far, the message for us has been that if you really want to imitate coordination, if you want to go beyond single agent systems and imitate coordination among the agents, we have to learn from demonstrations of interactions, whether it's in a form of behavioral cloning or reward learning or inverse reinforcement learning. It has to be that you collect data of interactions. But collecting data of multiple agents interacting with each other is not an easy thing to do. And you could arguably ask, why are you even thinking of imitation? Why don't you just use RL? Instead of collecting data and imitating policies, how about you just use multi-agent reinforcement learning to see how two agents learn to coordinate with one another? So we wanted to try that. And we were like, okay, let's take this same example that we just saw with two arms lifting the basket. Let's see what happens if I want to use RL for this same task. Here is our best effort, many, many rounds of reward shaping, to get these two robots to coordinate on this task through RL from scratch. And for some context, this is a simulation that my student, who's been spending 3 years of his PhD on reward shaping, and he knows a lot about robotics and he knows a lot about RL, but we couldn't find a way to get it to work through RL. And if you've ever worked in multi-agent RL, you know that what we can do with multi-agent RL is not even comparable to what we can do in single-agent RL. The applications of multi-agent RL in real world are very limited. So we started to think, we were like having this discussion of like, okay, why is it that we can't learn these policies through RL? How is it that we as humans learn to interact with one another? What makes us capable of exhibiting really, really complicated, subtle interaction strategies and coordination strategies in sports teams, for instance? Well, one of the reasons that maybe contributes to that is that we essentially have coaches for really hard interactions. And maybe that explains why coaches at the University of California are paid like orders of magnitude more than multiple orders of magnitude actually, than I'm paid. So we started to think maybe there is a room for us to coach robots into interaction. Maybe we can coach them to coordinate with one another. But how can we coach them? Maybe with all the success that we've seen from these large models, instead of just using these models to directly imitate action or provide actions to me, maybe I can just use these models as coaches for teaching the robots how to learn as a high-level, essentially, feedback provider. But let's think about what a coach does. What do I mean by that? When I was thinking about this, like let's think of a soccer coach, for instance. What is it that a coach does? First of all, a lot of the times, coaches develop curricula. They don't essentially give you the most complicated task to solve. They have a sequence of tasks that they have an increase in difficulty. They define for you what it means to do a task, like to do this skill, to do this drill, this is what you should be doing. And I define that as a reward generation. One of the really important things that a coach does is that they provide feedback to you. You execute something and they're like, nope, this part was right, this part wasn't right. And in a team effort, what a coach does is that they provide credit assignment. They're like, if this is a soccer game, this agent failed, the other did their job well. So we were starting to think, like, can we essentially have these models play the role of a coach in these aspects? Let me start by essentially the first one, where we're like, generate a curriculum and then sequentially increase the complexity of the task. And this is actually right at the time when Dorsa had his baby. And I was very inspired by watching Nib essentially trying on how to learn to walk. And we're like, clearly, he's just going through this curricula of tasks to learn. And we were thinking, let's just start with a single agent first and see if we can essentially do the same thing with robots, where I can teach, let's say, a humanoid or a bipedal robot to run through a sequence of tasks. And what we did was, there is nothing fancy here. It's just a language model. I asked it, break down the task of humanoid running for me. It was like, okay, first it needs to learn stability, then learn to walk, then increase the speed, then learn how to run with the target, the task. And then we essentially went through this, play the role of a coach, tell me what it means for basic stability learning, train on that, and then build on that, build on that, build on that. Nothing fancy here. No model retraining or anything. We just use off-the-shelf LLM. And the interesting thing to me was that we managed to essentially teach this robot to run backwards. And my colleague Kaushal, also he has an amazing lab on anything locomotion. He's the locomotion expert, and luckily his office is next to mine. So I was asking him, like, I went to the students, and I was asking, like, what can we do? What do you guys do for essentially training these policies? And they were like, here is this reward function, which is like a sacred thing. You shouldn't touch any of the parameters in this reward function. There are like 20-something parameters. This is just a result of trial and error over years. But then in 6 months, we managed to essentially teach this robot to run by essentially this proper coaching. And the interesting thing to me in this project was that you really needed it to break down the task into simpler tasks to learn a good reward at the end. Despite all our efforts, we could not just generate the reward, the final reward, one shot by even many more iterations. So we're like, great, now we could see that we can perhaps teach one robot to learn things on its own. How about now we coach 2 robots to learn, to interact and coordinate with one another? So here we had to make things a little bit more complicated because there was just too much that the coach needed to do. So we had like multiple, even our coaching system ended up being a multi-agent system. So we had a coach that breaks down the task, and then we have modules for essentially evaluating how the agents are doing each task, and then refining, providing essentially feedback and advice on how agents could improve upon the performance. And the training pipeline that we use in all of this is multi-agent RL, multi-agent PPO. So the algorithmic side hasn't really changed. And the same task that I showed you at the beginning, which was hopeless with RL, essentially they managed to learn something way better than what we had at the beginning. First, the agents align with the handle, then they grasp the handle, then they lift and balance the pod together. And this is all happening in a decentralized manner. So to remind you, with the proper coaching, this what you get is what you see on the right, but on the left, this is what you get with MAPO. Essentially, the robots don't do anything useful. Let me show you another example. Let's say you have two quadrupeds that one of them should balance a seesaw for the other one to climb the seesaw. This is something where we saw a lot of influence that the proper coaching has. Without proper coaching with MAPO, it just fails. But with the proper coaching and with the proper task breakdown, one robot learns to stabilize the seesaw so that the other one could essentially climb the seesaw. We can take it one step further. We can have quadrupeds that are essentially helping humans collaboratively transport objects. I just recently tried this demo myself, and I was amazed by how easy it is. The easiest way that I found you could just be working with this robot is just close your eyes, and it just helps you move things around. So it shows the potential to really even model and tackle tasks which are hard to essentially formalize. But what if I ask my coach to also provide credit for me? Credit assignment. What do I mean by credit assignment? Think of a task where I have two agents, Alice and Bob, and they want to essentially accomplish a task as a team. Each one of them has their own policies, Alice and Bob. They take actions, and they apply that action, and the environmental state evolves, and they get their reward functions. But let's say, hypothetically, they want to accomplish a task, like apple picking task, where the game is a little bit weird in the sense that some apples are such that they need both of Alice and Bob to essentially pick them up. But some of the apples are level 1 apples. They can be picked by just either Alice or Bob. But level 2 apples are the ones that need both of the agents to essentially pick them. Now, what happens when I'm training Alice and Bob to learn to do this together? When I train Alice and Bob, starting from scratch, let's say I have a level 2 apple. If Alice goes to a random place, but Bob goes to the right place, still the team fails. They can't pick the apple. So both of them fail. The team doesn't get any reward, doesn't get any credit. But Bob did the right thing. It's only that Alice didn't do the right thing. And if you don't take that into account, and you can't figure out which agent to essentially provide feedback to in your learning loop, then your agents will not learn. And that is called the credit assignment problem in multi-agent reinforcement learning. And I'm pretty sure, like, this is a challenge that every one of you faces at the end of the semester when you're working on a group project. Because as an instructor, I'm always getting this question. Literally today, I was getting emails that I worked in this team, but my teammate didn't really contribute. I did all the work. I should get credit, whatever, for the work that I've done. So we as humans are actually relatively good at credit assignment. I can show you these two figures, and I'd be like, who do you think is contributing to these efforts? And it's probably easy for you to see that. But that's really hard to do in the training loop of an RL algorithm. Like, how do you know who should get credit and who shouldn't get credit? So again, we were like, okay, people argue that these large models resemble human-like reasoning. How about we just use a language model simply as a critic within the training loop of a multi-agent RL algorithm? So I essentially roll out a policy and then give that policy or trajectory to my LLM, ask my language model, who do you think should get credit and who shouldn't get credit? Again, no retraining, It's just like, and at the time, this was a 2025 paper, the language models were not as good as they are today. So I think only things have got better since then. But we just asked that, play the role of the credit assigner for me, and then train through the usual multi-agent RL algorithms. And what we found was that these LLM critics result in a much, much better performance compared to the state of the art. So on the left, you see a robotic warehouse example where multiple robots need to coordinate to move packages. And on the right, I'm showing the reward versus different setups of the game, whether it's a small scene, medium scene, and for different number of agents. And the green curve is the reward that we are getting with our method, whereas the other ones you probably don't get to see well because the reward is so low is MAPO, QMix, and LICA, which are like one of the common state-of-the-art reinforcement learning algorithm, multi-agent reinforcement learning algorithms there. So we could improve the performance by orders of magnitude simply by using a LLM critic. And in fact, right now we are using a VLM critic, and we managed to see that we can, at least based on preliminary results, we can teach two humanoids how to work with one another. But so far, I think it's been exciting to me to see how far we can go by essentially using these foundation models as coaches. No fine-tuning, no training, just one shot, zero shot using these models has been quite effective, and just thinking about where it makes sense to integrate them within the learning loop of the robot. And I think we will be exploring this a lot more down the line. But in the interest of time, I just briefly talk about what we've been thinking about in the context of perception and interaction. In perception, we've been thinking a lot about how robots could collaborate with one another to map a scene using nerves. But thanks to, when I was a postdoc, I audited Mac's class when he was teaching distributed optimization, consensus ADMM particularly. And I never thought that like half of the projects in my lab right now are focused on distributed optimization and consensus ADMM, because it has turned into something really powerful, where we have seen that we can essentially do a much, much better job of mapping an entire scene collaboratively by combining these traditional tools with these more modern techniques like nerves and Gaussian splats. But more recently, and more perhaps I'm actually very excited about this very recent work, which is going to appear at RSS, we've been taking inspiration from what we've been doing in multi-agent perception. How can multiple agents collaboratively perceive an environment? And we've been really looking at the dual of multi-agent problem, and we've been thinking about how does multi-agent view of problems help with even a single agent problem. And particularly, we've been looking at continual learning, where you have a robot that is essentially collecting new data over time, and you just want to learn based on what you're getting. So we worked on this problem for quite a while because it was relevant to the coaching problem. You want to make sure you don't forget about things that you have learned in the past, but also learn new things. But one day in the lab, we had this realization that, you know what, continual learning, even for a single agent system, you can think of it as a multi-agent problem. If I don't want to forget about things that I've learned in the past, maybe I need to reach a consensus with the past versions of myself. Maybe I just want to keep reminding myself of like what I've learned in the past without having to essentially keep all the data that I've seen in the past. Just think about consensus over, let's say, my model parameters. And it turns out to actually give us some really good results in terms of how you can adapt to the changes, let's say, in the scene, while not forgetting about things that are the same. So for example, here, this is actually a real-world experiment that we ran, that, for example, I moved the yellow chair from point A to B. If I use replay-based methods, which keeps all the data, I end up with 2 copies of the chair. And if I want to use regularization-based methods, which regularize your model so that it doesn't forget what it has learned in the past, it doesn't adapt to the changes in the scene. But with a very simple ADMM-style consensus in the weighted space of your neural network, it kind of figures out what parameters of the weighted space it needs to change to adapt to these changes in the scene, and what parameters to keep constant. And just again, we've just been running these ideas in the context of attention and in VLAs, and we're seeing some really promising results by just being creative on essentially using these very well-known tools in that context. And on the safety front, I promised that I want to do safe and intelligent robots, but I didn't really get to talk about safety. We've been thinking a lot recently about how to enforce safety constraints within the training pipeline of these policies. How can we make sure that we have provable constraint enforcement in whether we have behavioral cloning policies or RL? We've just been using or thinking about provable constraint enforcement both in imitation and in RL. Here I'm just showing a video of like open loop diffusion when we actually directly enforce the dynamics of the robot in the diffusion generation pipeline, which manages to essentially give you dynamically feasible trajectories even for underactuated systems. But there's a lot that I think can be done in this space, and I think now that we are getting robots closer to the real world, essentially integration into our lives, safety considerations become more important than before. So with that, I would like to thank my students who actually did the work that I got to present here today, and the funding agencies that essentially supported this work. And thank you all for your attention. I'd be happy to answer questions. Yes.
The UTR thing, trajectory study. What were the units on the y-axis? How much better was it?
Good question. We were seeing roughly around like 30% improvement in the prediction accuracy. Yeah, I should have included those things. I'm getting back for the questions.
Really enjoyed the talk.
Thank you.
So in the segment where you talked about coaches, LLMs as coaches, how do you bridge that gap between language and quantified feedback, something that's numerical or functional?
That's a great question, and I think that's definitely a big part of it. For us, we've tried two things. In the one study, the bipedal robot, that was like very naive. We just gave the trajectories, like literally numbers to the language model, and somehow it figured it out. I didn't expect it to work. By the way, we started this project because I wanted to prove to myself that these systems don't work, but they worked. But then for the coordination part, one thing we found to be really useful was essentially give sequence of images, not videos. But let's say an image of how the robot did at the initial time, somewhere in between, and the final time. And that was the most kind of informative form of feedback, or the way of giving data to the VLM. But then we were very happy with it. But we tried another idea, and that turned out to be even more effective, which is we just gave literally the figure of the training curve. So we were like, okay, this is this component, or this is what this joint is looking like. And apparently, at least with the VLM at the time, I don't know about now, it was much easier for it, just giving the plot. And if you decompose your plots into, like, let's say, multiple components of your reward, let's say not the whole reward, but your reward has different features, and if you give the plot of every one of those features, that turned out ultimately to be the most effective, even more effective than the sequence of images. Why? I don't know. Yes.
Related questions. First is, what sort of data from human interactions would be useful if you had a lot of that? And then second is, what real-life problems between human-robot interactions have you noticed where some of these strategies would be extremely useful?
So I think I don't think I have a good answer to that question, because I think I'm not entirely sure if we fully know for sure, like in what ways are these problems different or in what ways they're hard. But I think the most valuable form of data in these is going to be the ones that have very tight coupled interactions. Let's say in the context of navigation, the most informative data that I can have is the collecting data about how humans behave when they get too close to each other. as opposed to just, a lot of data when they don't really interact with one another that much. I think the most useful form of data is when the coupling among agents' decisions is very strong, and that reveals the most about agents' preferences and what they have in mind. And I found this to even matter more if I want to do tasks which result in some physical constraint and physical coupling between the agents. Like if you and I want to transport a table here, there is this implicit coordination that is going to happen, which is really hard, and that it requires understanding force. Everything that we need to do in single-agent manipulation, now we need to do that in a multi-agent setup. But I think collecting that data is the most informative about how humans would like to interact. But one of the things that I find really hard when working with humans is that every human is different. I don't think I can't have like a nominal human model. And one other thing that I've noticed is that when you have a robot that works with a human, you ask the human, what do you think about the robot? When the robot is doing well, the human is like, it's just me, I'm great. But when the human essentially makes a mistake, the human results in the failure of the task. They're like, it's all the robot's fault. So it is this, I don't really know how to account for those. But for instance, we have a lot of the data of humans teleoperating the robots and collecting that and using that. But if it comes to their robot interacting with the human and asking for humans' preferences in those same contexts, I think there would be a huge diversity of how humans think. And then there are cultural aspects of it, social norms. I am not a human factors person, obviously. But I think that is why it's very important to actually learn from humans and to learn from them in a very sample-efficient way. Humans are not like simulators that you can collect a lot of data from them. It's you just want to be very quick and as sample-efficient as you can. So I don't really have a good answer for your question, but I think those are important problems to think about. Yes?
I don't think I quite understand how different robot agents are able to determine which one yields to the other. One who makes the first move. How does that work?
So that's a great question. Think of it the way that humans make that decision. And for a lot of initial conditions, for a lot of setups, it's kind of more efficient and more optimal for one to, let's say, yield to the left, the other yield to the right. But there are setups, the tricky setups are the ones which are perfectly symmetrical. And I think they also resemble scenarios when you are walking a hallway, you go to the left, the other person goes to the right, and then you're just stuck. In a lot of those times, you could think about, okay, if I just add something that breaks the symmetry for me, the robots could figure things out on their own. So luckily, in all the real-world applications, typically there is some form of an asymmetry that the robots will have to deal with. But very naive thing to do is just to add some noise to break down the symmetry. But as soon as the symmetry is taken away, the game-theoretic model, because the robots are optimizing for their cost function, it is kind of like a matter of you find out what is the optimal thing to do. And the optimal, because you are doing a game-theoretic planner, your decisions are aligned. If you don't account for what the other agent is doing, you're just optimizing on your own, ignoring the other, and who knows, that's going to work out. But because both of them jointly are modeling the other agent's decisions and response, they manage to align well. And that's a great question. There are always deadlocks that you need to watch out for, though. Yes?
In the project where you use LLMs as coaches for simulators, could you elaborate on where exactly they do the learning, where the LLMs fit in?
Yeah, let me actually go back to this slide. Where was it? Oh, here it is. So the LLM does this part for me. First, it breaks down the task, and it's just in language. It is telling me, what does it mean to go from when you know nothing to the target task. But then that same LLM is essentially translating each of these subtasks to essentially like a reward. Think of it as a reward generation for me. And the interesting thing is that because these subtasks are very easy, it's much easier for the LLM to come up at least with a good enough guess of what the reward should be. For example, if you say, I want to do stability. Maybe stability is something easier to define as a reward function. And then you iterate on that. You train a policy, and then you see, here we didn't even have a feedback loop. We were just like, sampled a bunch of policies and picked the best. So we didn't even have a model that provides feedback of the policy failed in this part, it should improve upon this part. But in the next part, here it was more kind of trickier to learn the policy. So we still had the curriculum module, but we have this evaluation part, which it is taking into account the learning curves. And then based on that, it gives advice. But in this stage, we needed to have two different models taking care of each one of these because it's just too much to expect from one model. So that's why I'm saying even our coaching system was a multi-agent system. Yeah. It was RL. Everything was RL in this context because we really wanted to see how far we can go with RL because RL is apparently not that common these days, at least when learning from scratch. Yes.
Just wonder at what point this can be at mass deployed. So what are can you summarize the key steps so that it can be deployed?
The coaching part?
Yeah, like the other technology was like coaching.
Yeah. So honestly, when I think about it, sometimes the fact that in academia we don't have as much compute as the industry has makes us be creative. Because we were like, oh, we can't really afford to do crazy training of these models. Like we were thinking about what are the ways in which I can just take an off-the-shelf model and use it and solve some of the problems that I'm facing. So 3 things that I've found out so far. One is task breakdown is very important. When I want to use these models in this context, I'm not. If I had different resources, probably my experience would have been different. So task breakdown helps a lot, and with the proper coaching, the choice of the RL algorithm and all those things doesn't really matter much. Breakdown of the task matters. Form of evaluation and how you provide input to your model such that it is understandable by the model to evaluate it makes a much bigger difference. And this is another line of work that we're doing, which is not published. We're just at the preliminary results stage. We have been thinking about, can I coach this, essentially use this coaching mechanism to train whole body controllers for humanoids. We've seen all this motion retargeting, collecting data from, I was like, okay, again, as an academic lab, we probably won't afford to do that. But there, this task breakdown becomes really important. And then the part which was the most critical was, what information do you give from your trajectory role as to your LLM or VLM, which is understandable by VLM, and you're not overwhelming your model by that. And in this case, we found the training curves to be the best abstraction and representation. But recently, these models take as an input videos too. I'm not sure. We just quickly tried it. It wasn't that effective, but maybe that has changed. But so you really want to iterate over how you provide information from your trajectory role as to your models. And then the advice part, in our experience, has been quite reliable. It's just, it iterates over things and reflects. So for me, I think the biggest thing is here. What to give it so that it has a good understanding. Yeah, but I don't know, maybe 2 months from now I have different thoughts. Yes?
How many diffusions of samples does it take someone here for reliable accuracy and precision?
Yeah, that's a great question. So none of the things that I showed are like high precision tasks.
Yeah.
And I don't want to make a claim on things that we haven't really tried. I assume that there you want your reward generation to be much more accurate, and you also want to, in that case, success rates need to be really high, and your policy should be very consistent and low variance. And that's typically hard to get with RL because there is some randomness inherent in it. So by no means I want to claim that this is going to be useful for high precision tasks. And I don't really know how it's going to work in that setup. Actually, yeah, that's something we've tried. With the humanoid one, we're actually trying that. And that turns out to be super effective. And actually, to the previous question, in my experience, at least, these models have performed the best when I ask them for these high-level decisions, not low-level actions. So we've tried like low-level model-based controllers, and that has been very, very effective, at least in the ongoing work. But hoping that the RL policy on its own with this could figure out an accurate policy, at least I don't, based on what we've seen, doesn't seem likely. Other people have done it, but we couldn't do it with this setup.
Do you have any intuition about what is the upper limit for the speed that might be generated, like in terms of like just the actions?
Oh, I see. So you're asking about the inference time that this might have. So keep in mind that this is all for training. At execution, I'm not using a language model.
Okay.
So this is just all happening. Once my policy is trained, it's trained, and I just deploy it. It's just during the training. But the training could take a while because you are querying the model and you want to be strategic in terms of when it is absolutely necessary to query your model. And one could argue, can you have specialized smaller models that their job is just to provide advice to you to make it be faster to integrate them in the learning pipeline? But training takes quite a while for sure. All right, I think that's it. Thank you, everyone. Thanks.